Hello everyone. Our next excipient is the antibacterial agent or preservative. Antibacterial agents are used in multiple dose injection where the vial is used several times like insulin vial. So the patient is entering the syringe or the needle several times inside the same vial. Every time there is a chance for contamination. In this case, we have to add something to stop the bacterial growth like bacteriostatic or antibacterial. It can be used also in the unit dose parenteral in the injection like ampoules or vials that is only injected at once as a single dose. But in certain cases, if the component or if the product is not terminally sterilized, if your suspension or your product is not sterilized after preparation. Sometimes we cannot sterilize certain dosage form after preparation. We have to sterilize the powder and the solvent or the water and mix them together under sterile condition. If we sterilize them after preparation, certain problem will happen, and this will come later when we talk about parenteral suspension. So if we are not able to sterilize the dosage form after filling and sealing of the vial, we are always doubtful of having contamination. So that's why we have to add antibacterial to make sure that there is no contamination happening during preparation. Also, for the rubber closure that is used for the vial, for this rubber closure, we are soaking this rubber closure in antibacterial before use, before adding it to the vial nozzle. So after adding it, this rubber closure will not absorb the bacteriostatic or the antibacterial from our product. So when the rubber closure become saturated with the antibacterial, it will not take antibacterial from the product. So we are preventing absorption of the antibacterial. Generally, we are using bacteriostatic, not bactericidal, because bacteriostatic, of course, which will stop bacterial growth but not kill it, it will be killed by time. It will go by time. But if we use bactericidal, it will be more toxic to our patient. So we are using bacteriostatic. But of course, the bacteriostatics that we are using should be used in a concentration greater than the minimum inhibitory concentration, the concentration that can inhibit the bacterial growth. Antibacterial or preservative cannot be used in intraspinal injection because whatever the amount that we are using, if we inject it inside the spinal cord, it will be toxic. And it cannot be used also in large volume parenteral because in large volume parenteral, the dialysis bag or the parenteral bag, for example, it contains 1 liter. This 1 liter requires high amount of preservative. To reach the minimum inhibitory concentration, we will need to add large amount of preservative. If we have 1 milli, we may add 1 milligram only in each milliliter to inhibit the bacterial growth. But if we have 1 liter, we may need 1 gram bacteriostatic. This 1 gram bacteriostatic, although they have the same concentration like the small vial, 1 milligram per milli is same as 1000 milligram and 1000 milli, or 1 gram per 1 liter. But here, the patient, after 1 hour or 2 hours or 3 hours, after taking this large volume parenteral, his body will be taking like 1 gram antibacterial or preservative, which could be toxic for the patient. But here, after injecting this 1 milli, the patient body will take only 1 milligram preservative. So the use of preservative is in large volume parenteral is not allowed because again, this large volume parenteral will require big amount of antibacterial, and this amount will be toxic to body. Another point, if we have an emulsion, do we need antibacterial in the oily component and in the aqueous component of the emulsion? No, because already in oil, bacteria cannot multiply. They will live but will not multiply, but in water, bacteria, of course, can multiply. So we really need the antibacterial in the aqueous component of the emulsion. So if we have two preservative, one is methyl paraben and the other is propyl paraben. Methyl paraben has low partition coefficient. It means it is polar, has more affinity to water, and propyl paraben has high partition coefficient. It means it is more lipophilic and has more affinity to oil. Which one is better to be used in emulsion? Of course, the polar one. Methyl paraben is better because we don't need a preservative that will stay in the oily phase. We need a preservative to stay in the aqueous phase because again in the aqueous phase bacteria can live and multiply and we have to stop this bacterial growth. There is a common incompatibility happen between the preservative and the surface active agent. You know that the surface active agent are having polar head and non-polar tail, and above certain concentrations they can form micelle. As you can see, the micelle is formed of different units or molecules of the surfactant. Each unit is polar head and non-polar tail, and this happen above the critical micelle concentration of the surfactant. That's good for the drug because the drug will be solubilized inside the micelle. But we have a problem here that some antimicrobial or antibacterial will be hidden inside this micelle, will be entrapped inside the micelle, and the portion which is entrapped inside the micelle will not be able to kill bacteria. It will not be able to come in contact with bacteria. Only the free antibacterial, if we have another portion which is free, this free antibacterial will be able to kill the bacteria. So again, if we have in the same preparation surfactant and preservative, part of the preservative will be hidden inside the micelle, and whatever hidden inside the micelle will not be effective. And the part of preservative that is outside the micelle is free, and this part is the only part capable of killing the bacteria. We have an equation to control that. Total preservative over free preservative. So here in this side we are talking about the antibacterial or the preservative. Equal 1 plus K, and K here is the slope of this line. This line, its slope is called K. And M is the molar concentration of surfactant. So what happened? Here, by increasing, of course, the molar concentration of surfactant, total over free become more, the whole fraction become more, its value is higher, but for the denominator, for the free version, for the whole number to be more, the free, it means it will be less. Like when you divide 10 divided by 5 and 10 divided by 2. This one equal, and 10 divided by 1, for example. 10 divided by 5 equal 2, 10 divided by 2 equal 5, 10 divided by 1 equal 10. You can observe here through this direction, when the number increase from 2 to 5 to 10, what makes this number increase? Because the denominator here is reducing from 5 to 2 to 1. So when I'm telling you when M increase, total over free increase from 2 to 5 to 10, total is a total. Total is constant. It means that the free fraction is reducing from 5 to 2 to 1. When the free is less, it means activity is less. Okay, so you can understand now, by increasing the amount of surfactant, the number of micelles become more and more. So it will entrap more preservative will be entrapped, and less preservative will remain free. Okay, so here, from another point of view, if you look at this graph, on the x-axis we have M. M is the concentration of surfactant, and the y-axis there is a ratio of preservative total over free. You can see the graph also by increasing M. What will happen to total over free? It is always increasing. Increasing total over free, it means less free fraction. Okay, but here we have different lines. Each line belongs to different preservative. If you have line A and line F, which one is better to be used, propyl paraben or benzyl paraben? Which one will have more free fraction? The one which will have more free fraction will be, of course, better because it will be more effective in presence of the same surfactant. So if you think like that, here, don't forget that K is the slope at the same concentration, at the same M. So let's think at this level. Here at the same M, let's start talking about, for example, propyl paraben. For propyl paraben, slope is higher than the slope of benzyl alcohol. You know, when the line is more vertical, it means that the slope is higher. If the slope is higher, it means K is higher. If K is higher, it means total over free is more. If total over free is more, it means that the free fraction is less and activity is less. So propyl paraben is not good, relatively not good compared to other. This is the worst one because again, at this M, slope of the line is higher and slope equal K. When K is higher, total over free is higher. When total over free is higher, it means that free is smaller. When free is smaller, it means it has less activity because most of the preservative now is entrapped inside the micelle. On the other side, what is the best preservative now? The best preservative now is benzyl alcohol because at the same molar concentration of the surfactant, this line has the lower slope, the lowest slope. When slope is lower, it means total over free is less. Total over free is less. Let's reverse all that. When slope is less, total over free is less. What does it mean? What makes this number smaller? That the denominator is higher. So we are going now in the opposite direction. The number is reducing, total over free from 10 to 5 to 2. It means that the denominator is reducing from 1 to 2 to 5, is increasing, sorry, from 1 to 2 to 5. So again, benzyl alcohol has the lowest slope in this graph. It means K is less, total over free is less. It means that the free fraction is higher and the effectiveness against bacteria is higher. To make sure that the preservative is working, we have to make a test like quality control test called the challenge test. We will bring our vial filled with suspension or solution or the dosage form with the preservative, and we have to test it near, all over of course, the shelf life, but near the expiry date, especially near the expiry date. And we will open the vial under sterile condition, of course, but we will add bacteria, certain concentration of bacteria, known amount of bacteria. And we will keep it for a time, and then we will count the bacteria. If the number of bacteria is increasing, it means that the preservative is not working. We have to find another preservative or to increase its concentration. If the number of bacteria is same or less and the bacterial growth stop, it means that the preservative is good, and we have to make sure that the preservative is good until the end of the expiry date, till the last day of the shelf life. Another excipient now we have is buffer. Buffer is added to resist change in pH, and you know from the previous slides that pH is very important for the drug solubility and the drug stability. Most buffers are made of weak acid and its conjugate base. Of course, it could be also weak base and its salt, but mostly it is weak acid and its salt. The salt here is called conjugate base. So we have examples here like acetic acid and sodium acetate. So that is the weak acid, and that is the salt, which is called conjugate base, and so on. Boric acid, weak acid, and that is the salt or the conjugate base. Citric acid, sodium citrate, phosphoric acid, potassium phosphate or sodium phosphate. So that are example of weak acid and its conjugate base. Uh, Here we have this acid is able to interact with any alkali present. If you add alkali to the solution with this buffer, so the alkali will interact with phosphoric acid and phosphoric acid will change to potassium phosphate. If you add acid like HCl, it will interact with potassium phosphate and phosphoric acid will be formed, which is weak acid. So that's why this will maintain the pH as much as possible when you add a strong acid or a strong alkali. And the magnitude or the amount of resistance to change in pH is called buffer capacity. So some buffers has high buffer capacity or high beta, and some buffers has low buffer capacity or low beta. So this buffer capacity equation beta equal delta B over delta BH. Delta B is the amount of base or acid added to 1 liter of buffer solution, and delta BH is the buffer change. When you add much acid or base and pH are not changing, delta pH changing pH is very less, from 7.2 to 7.3. It means that the buffer capacity is very high and that could be ideal to stabilize our drug. If you add small amount of acid or base and this led to huge change in pH from 7 to 11, it means that the buffer is not good and buffer capacity is very low. So our main aim or our main target for adding the buffer is to maintain constant pH during storage before injection, because if the pH changes during storage, it may lead to degradation of the drug or precipitation of the drug. But after injection, we don't want to keep the pH away from the body pH, because in this case, the injection will be very irritant. We have to allow the body fluid to neutralize the pH. If our injection is stored at pH 11, okay, we need to keep it 11 on the shelf life before injection. That's very important for stability. But for irritation, after injection, we need this pH to go down to 7 or 7.4 immediately. Otherwise, it may cause problem. So, if the pH of our preparation is far from the pH of the blood, we should not use very high buffer capacity. Because if pH is 11 or 2 away from 7.4, we should use low buffer capacity. Okay, we are using buffer with buffer capacity to maintain it stable outside the body, but after injection, we need to enable the body fluid to neutralize the pH. We need to allow our blood to take this pH down rapidly to 7.4 to avoid any problem. But if the pH of our preparation is very close to blood pH, for example 7.3, in this case we can use very high buffer capacity, because 7.3 from 7.4 is not so far, so we can use buffer with high buffer capacity in this case. In case of ophthalmic preparation, the eye fluid amount is very less, so we cannot use buffer with high buffer capacity at all, even if the pH of our eye drops is 7.4. Even if it is very close to the physiological pH, we have to use low buffer capacity. If you use a high buffer capacity, in any case, it will be irritant, because again, the capacity and the volume of the tear fluid is very small. So again, to summarize that, if you are having parenteral injection, you have two choices. You may use high buffer capacity if the pH of the injection is near or close to the pH of the blood. You should use low buffer capacity if the pH of the injection is far from pH of the blood. The third option, in case of ophthalmic preparation or eye drops, you have to use low buffer capacity regardless the pH of the preparation, because if you used high buffer capacity, it will lead to irritation. We have examples that we have been using it like borate buffer and phosphate buffer. Each one is suitable for certain route of administration. For borate buffer is very weak buffer. Buffer capacity of borate buffer is by default is very low. So that's why it is very suitable to be inserted in the eye. And the problem also that cannot be injected in the body because it is toxic. When it's taken systemically in the blood, it is toxic. But when it is added to the eye, topically in the eye, it's very safe. So borate buffer can be used only in ophthalmic preparation and eye drops because it has low buffer capacity by default and cannot be used orally or parenterally because it is toxic. On the other hand, phosphate buffer is very safe, either in the eye or in terms of toxicity, of course, and or injection. But by default, compared to the eye, it has high buffer capacity. So it is not toxic. It can be injected. It is taken by parenteral route, but it cannot be inserted in the eye because by default, phosphate buffer, it has high buffer capacity and it may lead to irritation in the eye. So borate buffer is more suitable for the eye, phosphate buffer is more suitable for injection. Another excipient is chelating agent, and chelating agent is added to inactivate metals present in our preparation. Of course, we are not adding metals in our preparation. Heavy metals is present in the preparation is coming as impurities from the raw material, from the rubber closure, from solvent, from container, from any source. So and this heavy metal can catalyze oxidation. So especially if our drug is liable to oxidation, presence of air and heavy metals will facilitate this oxidation. In this case, we have to add ethylene diamine tetraacetic acid or citric acid and tartaric acid to chelate and hide the metal and inactivate it. Another also excipient that should be added if the drug is sensitive to oxidation is inert gas, as we mentioned before. That presence of oxygen in the solution and in the headspace also will facilitate oxidation. So to avoid that, we have to remove oxygen. How? By boiling the solution if it is thermostable, if the drug is thermostable, to reduce the oxygen present in it because you know the temperature of solubility of gases in water decrease by heating. And also after boiling, we have to purge, it means pushing nitrogen or carbon dioxide inside the solution and inside the headspace. So now the solution and the headspace will be full of carbon dioxide or nitrogen, which are inert gases, and that's how we can protect our solution. Another excipient is the surface active agent, and you know that surfactants are added mainly to enhance solubility. To enhance solubility, surfactant has to make micelles, and this should happen above the CMC. So if you are adding surfactant to enhance solubility, its concentration should be above the CMC. And you know also that surfactant has two categories, aqueous or polar and non-polar. That is based on HLB. If the surfactant is having low HLB, it means it is lipophilic and it can stabilize oily solution or solubilize drugs in oil in another way. If the surfactant is having high HLB, high value above 10, 15, 20 or sometimes more, it means it is hydrophilic or polar and it can solubilize drug in aqueous solution or in water. We have example from the market, steroid drugs, hormones are solubilized by tween and span or mix between tween and span. Tween is polar, span is non-polar. And amphotericin B, which is one of the most common and old also antifungal, is commercially available solubilized by sodium deoxycholate, which is one of the bile salts present originally in our GIT, but we are using it now here as external excipient. So sodium deoxycholate again is another excipient used to solubilize amphotericin B in water. There is another use for surface active agent in suspension. In parenteral suspension, we can add surfactant not to solubilize the drug, just to stabilize the suspension and prevent caking. So it will be absorbed on the surface of particle, the suspension particle, and remain on it and prevent caking. In this case, we have to use the surfactant in a concentration below the critical micelle concentration. We don't need micelle. If we make micelle here, this micelle will solubilize the drug, and we want to keep our suspension as suspension only. The most common surfactant are always non-ionic surfactant. It's better than the cationic. Cationic is the worst. Better also than the anionic, the one with negative charge. So the most common and the best, the safest one is the non-ionic, and the common examples are sodium deoxycholate, as we said, twin, span, poloxamer, or polyuronic. One of the most common excipients also, or surfactant, and lecithin. Very important excipient here, which is the isotonicity adjusting agent. We have to understand first, before talking about this excipient, we need to know what is osmosis, or to remember what is osmosis and osmotic pressure. If you have a semi-permeable membrane, and around on the both sides of this semi-permeable membrane, here there is dilute solution, and here there is a concentrated solution of any drug. Diluted solution, it means it has more water, and concentrated solution, it has less water. Semi-permeable membrane allow only permeation of water without any molecules. So by diffusion, as you know, the diffusion is happening from high to low. Diffusion of anything in our life is happening from higher level to low level. If water is the only component allowed to pass, so water will move from which side to which side? From the left side to the right side, from the diluted side to the concentrated side, because the diluted has less drug, okay, but has more water, and the concentrated has less water. So osmosis, that is osmosis. Osmosis is a solvent movement through a semi-permeable membrane from the diluted solution into a concentrated solution. Because of what? Because of the difference in concentration. This difference in concentration is called osmotic pressure. So osmotic pressure is the pressure responsible for movement of solvent from one side to the other side because of the difference in solute concentration. So it's very important in our parenteral injection to know if our product is having the same osmotic pressure as red blood cells or having different osmotic pressure. The amount of solute dissolved in our preparation should be the same as red blood cells. If our solution is more concentrated than the red blood cell, more concentrated, it means hypertonic. If it is hypertonic, it means having higher solute concentrations than the red blood cell. So if that is the red blood cell, has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But that is the red blood cell. 10 solute, let's take it as an example. And our preparation has more than 10. Very concentrated solution with drug. I know that the red blood cell has other component, not drug. But whatever the substance present, if the solution here is more concentrated than the solution inside the red blood cell, the wall of the red blood cell here acts as a semi-permeable membrane. Semi-permeable membrane. So it will allow movement of the fluid, the water, from the diluted side to the concentrated side. So water will move from inside to outside by osmosis. This will make shrinkage of the red blood cell. Shrinkage is not toxic, especially if this shrinkage is reversible and will not stay for a long time. But of course, that is not ideal. So injection of hypertonic solution could be acceptable if the shrinkage is taking short time and reversible. But if it's continuing for a long time, if you are injecting large volume of hypertonic solution over many hours, it will affect the physiology of the red blood cell. If we inject hypotonic solution has lower concentrations than the red blood cell. So that is the red blood cell also has 4, 5, 6, 7, 9, 10. And our solution outside has 4 molecules only. So our solution has more water and the red blood cell has less water. And this membrane now acts as a semi-permeable membrane. So water will move from outside to inside. And this red blood cell will start to swell till it explodes, or swell and explosion. This will lead to hemolysis of the red blood cell. So the patient is losing this red blood cell, and within a short time, this will lead to hemolytic anemia. So we cannot inject hypotonic solution, especially if it is a large volume for a long time. Otherwise, the patient will suffer from severe hemolytic anemia. So the ideal way of injection is to inject isotonic solution. Hypotonic will cause shrinkage of the red blood cell, which could be acceptable. Hypotonic will lead to a rupture of the red blood cell and the explosion of it, hemolytic anemia, which is very bad for the patient, especially if it continues for a long time. But injection of isotonic solution is ideal, because if the red blood cell has this number of molecules, 10 for example, outside also it will have 10. So water will not move from outside to inside or from inside to outside. The net movement is 0. We have example from the market, which is saline solution, 0.9% sodium chloride solution. So the problem is, if we prepare our solution now and our solution is hypotonic, we dissolve the dose. Drug dose is 1 milligram in 1 milli. So it's very diluted solution. The drug is 1 milligram only, and there is no other excipient. And our solution now is hypotonic. How to make it isotonic? How to increase the concentration of solutes inside this solution? Of course, we cannot add more drug, because adding more drug may be toxic to the patient, because it is overdose. The dose is 1 milligram only, and the drug is potent. We cannot put 10 milligram or 100 milligram to adjust isotonicity. Of course, it will not be irritant after adding 100 milligram, because it is isotonic. It is not irritant, but it will kill the patient, because it is 100 times the required dose. So the only solution is to add another substance, inert substance, to adjust the isotonicity. It is inactive, of course. We can add sodium chloride, we can add dextrose, mannitol, any other sugar or salt, inert substance to adjust isotonicity as much as we need. There is no problem. It is inactive. It doesn't have any pharmacological action. So if we need 100 milligram solute in our solution for the solution to be isotonic, and the drug dose is 1 milligram only, so we will add 99 milligram isotonicity adjusting agent, and that is the excipient that we are talking about. So the excipient here is called isotonicity adjusting agent. It is inactive excipient added along with the drug and other excipient, just to convert the solution from being hypotonic to become isotonic. The last excipient we have today is cryoprotectant or lyoprotectant. Lyophilization, it is used to stabilize drugs converted from the aqueous phase or the solution to be a powder, to extend the shelf life of this solution, especially if you have protein drug. So if when you convert it to powder, it may become more stable. But the problem during freezing and the drying, which is lyophilization, what will happen? Before lyophilization, protein which is present in water is stabilized by making hydrogen bond with water. So we have hydrogen bond with water molecule. This is the protein making hydrogen bond with water molecules. The problem is, when you evaporate water during lyophilization, when you remove water, protein will not be bound to water. Protein will bound instead of that to other molecules of protein, and protein will start to agglomerate and make caking and become denaturated and inactive. So during drying, the problem is when you remove water, protein become aggregated together because it will make hydrogen bond with each other and become denaturated. So when you remove water, we need to replace water during drying with some other substance that can make hydrogen bond. And that is called water replacement theory. So the good stabilizer or the good cryoprotectant or layer protectant could substitute water in making hydrogen bond with protein. So instead of water, there was water here. When you remove water, cryoprotectant will come and make hydrogen bond with protein. So instead of the protein being stabilized by hydrogen bond with water, it will become stabilized by hydrogen bond with cryoprotectant. That's why you will find the examples are full of OH. So they are all capable, or NH2. They are all capable of making hydrogen bond. Any group that can make hydrogen bond, like sugars, sucrose, lactose, trehalose, polyols like glycerol, even it's called polyols. It has several ols or several OH, mannitol, sorbitol, amino acids, and some other polymer like polyethylene glycol, dextran, and polyvinyl pyridine. Thank you so much and see you in the next chapter.